All right, so we're starting into Chapter 9 today. So we're going to, let's get going, guys. We're going to spend a couple days talking about sequences. So let's think about if we're talking about sequences, what are we talking about when we're working with sequences? So when we say a sequence, what do we mean? A group of numbers. Okay, that works. A group of numbers, and usually when we're working with sequences, how are they related?
Some kind of like pattern.
Okay, that's perfect. So we're talking about some kind of group of numbers, and there's some kind of pattern. And usually when we write a sequence, usually there's the pattern. There's some kind of order in this group of numbers. So that's our kind of the way we think about sequences. Some kind of group of numbers with a pattern. We're going to make our definition. Come up with a definition that's a little more strict, but essentially means the same thing. So we're going to define a sequence, and I have to make sure I spell right here. So we're going to define a sequence is a function whose domain is a set of positive integers. So the function is what gives us our numbers, and the fact that we have a function, we're plugging in positive integers. That's what gives us our pattern. So we have this function, we plug in our integers, and we get this pattern. And rather than function notation for sequences, we usually use subscript notation. So we're going to say, rather than f of 1, f of 2, f of 3, we're going to say a1, a sub 2, a sub 3, all the way up to how far we're going, a sub n. And we call these are the terms of the sequence. And when we refer to the entire sequence, so the entire collection of these numbers, we put the a sub n in brackets. The braces, I guess. So this would be how we refer to the entire sequence, the entire collection of these numbers. And if we just write a sub n, a sub 2, a sub 5, whatever, that's just a single term of our sequence.
We invalid term numbers if it's not a positive integer.
Right. Okay. So yeah, our subscripts are always going to be positive integers. Sometimes we'll use 0. We'll use 0 as a subscript, so we'll use the positive integers and 0. So I guess in that case we'd say non-negative integers. But this definition will hold us for what we're doing. So just for notation, a sub n is a term. The entire sequence is in braces. So we can give a rule for how we write our sequence, and then we could write out each term of the sequence by plugging in numbers for n. So we could say, I'm not going to write everything out, but an example would be we could define a sub n, for example, as 2 to the n. And we plug in n equals 1, n equals 2, n equals 3 to get our terms of our sequence. So that would be one way to define, and we call this defining the sequence explicitly. We can also define our sequences recursively. So if we define them a recursive sequence, so if we want a recursive sequence, we usually need one or more of the first few terms, and then later terms are defined in terms of their earlier terms. Have to use terms a lot here. The terms are defined in terms of the first few terms, usually with a recursive sequence. So an example of a recursive sequence, we could say that, just as a recursive sequence, a sub 1 equals 3, and a sub k plus 1 equals 2 times a sub k minus 1. And we can write out the terms of our sequence.
Do we need a sub 2 then as well?
What's that?
Wouldn't we also need a sub 2 then in order for that to work?
Well, we can get a sub 2 from this. So we could say a sub 2 would be 2 times 3 minus 1.
Well, to get a sub 2, then k would be equal to 1.
Right. So, and I have.
We need a sub 0.
Well, I have. I'm starting with a sub 1. I have a sub 1.
Yes.
So I can plug a sub 1 in here to get a sub 2.
But 1 minus 1.
It's not
a sub k.
Yes.
Separately minus 1.
Yes.
Okay.
The term minus 1, not the subscript minus 1, but the entire term minus 1.
That makes sense.
Okay.
Sorry.
All right. So a sub 2 would be 4. A sub 3 we plug in 2 times 4 minus 1, which would be 6, and we could keep going. And then we could figure out the terms of our sequence. And often you can have recursive sequences that are defined in terms of 2 or more previous terms. Then you just have to know more previous terms to get started. So we all good with our notation and what when we're talking about sequences, what we're talking about. Okay? So in your book, on page 602, we're looking at numbers 15 through 20. We want to match, it gives a definition for the sequence, and we want to match the sequence to its graph. So take a look at those. I'm sorry, no, I think 15 through 20. So we're matching the graph to the sequence. So they give you a definition of the sequence, and they want you to match it with its graph. So let's take a minute to look at that, and then we'll go over these.
Exactly.
All right, so graph A. Graph A. Which number does that match up with? 16. Does everybody agree? A matches with 16. And so, how did you go about choosing? What tools did you use to analyze this? Plug in some numbers. Wait, Sean said limits. Right. So take the limit as approach infinity. You can see that one goes to 0. Oh, I'm sorry, not 0. Goes to 8, right. And you could use L'Hopital's rules to figure that out. All right, how about graph B? Which one does graph B match up with? Graph B matches 18. Do we all agree with that? Isn't that interesting what that graph with the factorial ends up looking like? I find that kind of interesting. Number 20, which one does that match up with? See, I kind of gave it away. C matches up with number 20. It has to alternate positive and negative, and it gets smaller and smaller. How about graph D? 19. It just alternates between positive 1 and negative 1. Graph E. 17. Does everybody agree on 17? And then graph F has to match with 15. How did you determine between? How did you pick between E and F? They kind of look the same.
You said E hits 0.
At 7, F hits 1.
So you compare points and said, does this work or does that not work? Okay. And you could also look at limits, or for number 17. If you looked at 17, that's a geometric sequence, and you can figure out what your limit is there. So is everybody good with matching these graphs to their sequences? All right. Let's talk about another concept, the limit of a sequence. What do we mean when we say the limit of a sequence? So what do you think we're talking about when we're talking about the limit of a sequence? What it's approaching as it approaches infinity. So does it come? Is there some value that doesn't get above or below or something? The main point of this entire unit is determining whether sequences, and we'll talk about series, whether they converge, whether they approach a limiting value. So that's really the central topic of this unit. And limits are really the central topic of calculus, the idea of a limit. So whenever we talk about limits, we're kind of getting to the heart of calculus in general. So let's give a strict definition of what we mean by the limit of a sequence. And this is one of your favorite things. So we're going to say that L is a real number. The limit of our sequence a sub n equals L, or the other way that we write it is the limit as n approaches infinity of a sub n equals L if, are you ready? For each epsilon greater than 0, no matter how small, there exists an M greater than 0 such that n greater than m implies that the absolute value of a sub n minus L is less than epsilon. if the limit exists, oh, greater than 0, sorry. If this limit exists, the sequence converges. So if this limit exists, we say the sequence converges. And if the limit does not exist, then the sequence diverges. So we get to this is our formal definition of a limit for a sequence. So we have this epsilon greater than 0, no matter how small. So for any epsilon, no matter how tiny we pick our number, we can find an m such that when our terms of our sequence, when n is past m, then our terms of our sequence are within epsilon units of our limit. And we'll draw a graph here in just a second to show what this means. So this is our formal definition of a limit. And this brings us back to the joke that I told the other day about the shortest math joke in the world. Assume epsilon is greater than 1. So in math, usually we're saying epsilon is extremely small. So that's why that's a joke. We're assuming epsilon is greater than 1. Just let it sink in. It'll get funnier as you one day when you're getting ready to graduate from college, you'll be saying, that really is a fun joke. So we're not going to. I'm not going to make you guys do epsilon proofs with sequences, but I just want you to know that this is our formal definition of a limit. This definition of a limit is really what allowed for a sequence, for a function. It really is what allowed calculus to be made rigorous. Is this definition of a limit? Yes.
How can, if this is the definition for a limit, how can you use the word for limit in the definition? Wouldn't that make it? Because it says, if this is the definition for a limit, then in the definition it says the limit of a sub n equals L. So wouldn't that assume you already know what a limit is?
L is the limit.
L is just some number.
Okay.
So L is just some number. So we're saying we're defining the limit as this number,
L.
right? Some number L, if these conditions hold
All right.
on L. So then we can define. Then we can say L is the limit.
Well, it's still the same as using words for limit.
So yeah, we can say L is a real number.
That's true.
A sub n is L, and we can say that the sequence equals L, given this, and then we would say then L is the limit. So we could be a little more precise in the language here.
It's fine.
Okay, so let's draw a picture of what this is telling us. Graphically, what this definition says. So here are our axes. And for a sequence, it's kind of nice because graphically it's relatively easy. So on this axis we have n, and on the y-axis we have our a sub n. And we're going to say that L, our real number, is here, and up here is L plus epsilon, and down here is L minus epsilon. And I'm going to come out here like so, and I'm just going to extend that, and I'm going to extend this. And here we have n equals 1, n equals 2, n equals 3, and we go out, and finally we're here at n equals m. So, and here are the terms of my sequence for n equals 1. Let's say I'm up here. for my a sub n. For n equals 2, I'm down here. Say for n equals 3, I'm up here. For n equals 4, I'm down here. For n equals 5, say I'm up here. And then eventually, all my a sub n's, and I could, let me do this a little. I'm going to go down here. I'm going to go just up here a little bit. And eventually, when n is past m, all my a sub n's are within epsilon units of L. So eventually, my terms can be bouncing around here, but eventually when I get to m, they can still bounce around, but they're within this band of L plus epsilon and L minus epsilon. And we can pick epsilon as small as we like. So we could pick epsilon to be 1/10 billionth, and then if our sequence has a limit, eventually we can find an m such that our terms of our sequence would bounce around within L plus a billionth and L minus a billionth. That's what our definition is telling us. So I'm just going to write for n greater than m, a sub n all a sub n lie within epsilon units of L. So that's what our definition is telling us. And if we can find this m given some tiny epsilon, then our limit exists. So let's talk a little bit about how we're going to work with limits, and then that's really all we're doing with sequences today. So if we have the limit of a sequence, we're looking at the limit of a sequence. We've defined it. Let's look at a little easier way to work with the limit of a sequence. So let's let f be a function such that the limit as x approaches infinity hard time with infinity here. There we go. That the limit is L. If we have a sequence if our sequence where the terms of the sequence match our function value, where f sub n equals a sub n for all n, then our limit of our sequence is L. So this is part, when you were working with the graphs, this is kind of what you did with those graphs. If you were looking at the limits, you looked at the definition of the sequence, you thought of that as a function, and you said, if I can find the limit of this function, I can find the limit of the sequence. So you were kind of intuitively doing that already. So all this tells us is if we can figure out a function where the function value agrees with the term of the sequence for each integer, then I can just look at the limit of that function and say that's the limit of the sequence. So that gives us an easier way to work with limits of sequences. We can work with what we know with limits of functions. And let me give you a quick reminder of properties of limits, and then we'll be done. So just a quick reminder for working with limits, just in case. So we have the limit as n approaches infinity of a sub n is L, and the limit as n approaches infinity of b sub n equals k. And I'm going to, just to write these out, we're going to assume that we're talking about the limit as n approaches infinity. I'm not going to keep writing it down. I'm just going to write it as limit. So the limit of the sum or the difference of our sequences is just the sum or difference of the limits. And we're assuming that we're talking about the limit as n approaches infinity for all of these. If we take the limit of some scalar multiple, or some multiple of a sub n, is just the multiple times the limit. Yeah, c is just a constant. So we're multiplying the each term by a constant. Then our limit is just the constant times the limit. So c is just a real number. C is a constant. The limit of the product is the product of the limits. And the limit of the quotient is the quotient of the limits as long as our denominator is not 0. And we're going to say that b sub n not equal to 0. So just a reminder of our properties of limits. Questions? So the homework today is just practicing with sequences and kind of getting us back up and running, working with sequences and limits and thinking about these things. All right. Whoops, not page 41. There you go.